Hello my friends and welcome back to the You Can Do TV channel.
Many people imagine concrete demolition as uncontrolled smashing. The Brock 500 removes a thick, reinforced wall while leaving a precise perimeter of rebar intact. The demolition robot moves its hydraulic arm toward the surface and presses a pointed tool into the concrete face. Instead of smashing the structure, the tip pries and fractures sections so chunks detach from the wall. Spray nozzles release a steady mist over the working area, cutting most of the dust produced during removal. By the final passes, the concrete barrier is gone, while the surrounding rebar frame remains prepared for the next structural connection. A custom curb roller drum forms an entire concrete drainage ditch in one continuous pass. Crews prepare the base path first, so fresh concrete can spread evenly along the trench. The custom drum then mounts onto the curb roller and rolls forward across the wet material. Its formed steel surface presses both sides of the ditch into the designed angle, while excess concrete moves outward along the edges. One pass replaces several forming steps, which saves time on complicated ditch layouts. Concrete slides under the drum like dough under a rolling pin, only this version weighs a lot more. Workers guide the machine steadily so the ditch wall and channel lines stay uniform. By the end of the run, the drainage shape stands complete in a single formed section. A 105-year-old cotton mill meets its final chapter under controlled demolition equipment. Concrete cutters slice structural sections first, so the surrounding area stays stable during the collapse plan. Excavators then approach the structure, guiding crushing jaws into the brick and concrete frame. Layer after layer separates while steel supports fold inward toward the cleared drop zone. Debris spreads across the ground in controlled sections rather than uncontrolled collapse. You suddenly realize how much material one structure can hold after a century of use. Water spray systems operate through the work zone to reduce airborne dust as the structure disappears piece by piece. Part of the wall falls away, and the whole scene suddenly feels like history being folded shut. Heavy machinery continues pushing debris into piles so loaders can move broken brick and concrete toward recycling or disposal areas. By the final stage, the mill that stood for more than a century is reduced to sorted rubble prepared for removal. Road surfaces split apart under traffic and weather. Yet gap-mastic crack repair handles wide pavement fractures with a flexible seal built for movement. The repair zone is first cleaned so dust, loose asphalt, and debris no longer block adhesion. Heated gap mastic is then placed into the wide crack, filling the cavity and bonding to the surrounding asphalt. The compound spreads across uneven edges and settles into deep sections that standard sealants often fail to reach. Fresh material pushing into every corner feels like watching a puzzle piece finally slide into place. A leveling pass follows, shaping the surface so vehicles roll across the repaired section smoothly. Whoa, that wide fracture suddenly looks manageable again. Flexible structure allows the sealed crack to shift with pavement movement, rather than split apart again. Hydropower capacity reaching 16 gigawatts emerges from the colossal arch dam construction, supporting 16 giant generators. Steep slopes along both banks undergo stabilization before the dam body rises. Rock faces are excavated in stages, cutting down to planned elevation lines that prepare the foundation zone. Huge sections of hillside disappear step by step. After slope treatment, massive concrete placements gradually shape the arch structure. The size alone feels unreal. Each section locks into the curve designed to channel water pressure safely toward the canyon walls. .9 kilometers of railway track undergo removal and rebuilding within a tight construction window. Excavators move in first, stripping away aging rail sections and concrete sleepers that held the old alignment for decades. Hydraulic breakers crack stubborn foundations while loaders carry the debris away. Crews continue by clearing the ballast bed, exposing the compacted ground beneath the line. Fresh layers of crushed stone spread across the corridor, forming the base that supports the new railway structure. Rail sleepers are arranged in long rows across the prepared bed. Steel rails follow, lowered into position and fastened onto the sleepers through fastening systems that lock each segment firmly in place. Every piece must sit perfectly straight, otherwise the next train would immediately reveal the problem. Additional machines align the track geometry, adjusting spacing and elevation across the entire rebuilt section. Compaction equipment presses the ballast tightly around the sleepers, stabilizing the track body for heavy traffic. The corridor transforms from scattered rubble into a clear railway path, in what feels like no time. Drainage ditches appear along both sides of the route, guiding water away from the track base to prevent structural weakening. Service paths beside the rails provide access for inspections and maintenance equipment. Old railway materials are gathered and transported for reuse or recycling. Seeing an entire rail corridor renewed piece by piece carries a certain thrill: steel, stone, and machines rewriting the path of travel. Consider the challenge of stabilizing loose ground. Liebherr LB24 and LB28 drilling rigs create secant piles using segmental casing to hold the borehole open. Rotary drilling heads drive the casing downward section by section, each steel segment locking into the next as torque transfers through the stack. Segmental casing prevents loose ground from collapsing into the borehole, a simple idea that solves a huge stability problem. The drilling tool removes soil from inside the casing, while hydraulic systems rotate and press the assembly deeper into the ground. New casing segments arrive continuously, extending the column until the required depth is reached. The growing tower of steel sections almost resembles a mechanical telescope pushing into the earth. Once the borehole reaches its final depth, reinforcement cages are lowered into the opening. Concrete is then poured inside the casing, surrounding the steel reinforcement and forming the structural soldier pile. One drilled column suddenly becomes part of a massive underground wall. Machines repeat the cycle along the excavation line, positioning piles at calculated intervals to create the secant barrier. The casing segments are gradually extracted, while concrete fills the void, leaving a solid vertical column locked into the soil. A row of these piles quietly turns loose ground into a controlled construction zone. A single rail bridge span can decide whether an entire railway line reopens on time. During a tightly scheduled possession window, a 30-meter rail bridge must rise into place before trains are allowed back onto the track. The task centers on constructing a new bridge structure that allows the railway to pass over a newly built bypass road. Every activity during the possession period is planned down to the hour. Miss the window, and rail traffic waits. No pressure at all, just an entire timetable standing behind the clock. Work on site prepares the ground for the bridge long before the span arrives. Excavation machines shape the foundation zones where concrete abutments will support the structure. Formwork panels rise around reinforcement cages, and concrete fills the molds to create the load-bearing supports. Concrete might look simple, but each dimension quietly determines whether the bridge will settle exactly where it belongs. Once the abutments gain sufficient strength, delivery vehicles bring the steel bridge span to the work zone. The structure measures roughly 30 meters across, large enough to clear the roadway passing beneath the railway. The span rests temporarily on transport supports positioned near the track alignment. Huge steel segments resting beside the track have a way of reminding everyone how small people look next to infrastructure. Crews prepare a sliding installation system. Temporary rails, rollers, or skid beams form a controlled path between the staging area and the abutments. Hydraulic jacks and pushing equipment provide the steady force needed to move the structure. The bridge then begins its slow movement toward the track corridor. The steel span glides forward across the prepared sliding system, while crews monitor alignment along both sides. 30 meters of steel drifting sideways toward the railway makes the entire site pause for a moment. Gradually, the span crosses the gap above the new road. Small adjustments guide the structure until the ends line up directly above the bearings mounted on the concrete abutments. The sliding motion continues until the bridge settles into its final position. Once seated on the supports, crews secure the span and prepare the deck for railway installation. Ballast is distributed across the bridge surface, creating the base layer for the track structure. Sleepers are arranged across the span, followed by steel rails that reconnect both sides of the railway. Track machines move along the rebuilt section to stabilize the ballast and correct the alignment. Measurements confirm the rails meet the required geometry before the possession window closes. Final inspections check the bridge structure, track fastenings, and surrounding work areas. With everything confirmed, the railway line becomes continuous again, now carried safely above the road below. Heavy steel, sliding systems, and a deadline that refuses to wait, railway bridge work, always brings a little tension to the timetable. Coal seams hundreds of meters underground are carved apart by the long wall shearer, while roof supports march forward behind it. Transport units such as the diesel manned car and drift runner manned car carry crews through the tunnels, reaching the centenary muster area before the shift moves deeper into production zones. Development headings rely on the miner and shuttle car system. The miner cuts directly into the coal seam, while the shuttle car moves in to receive the material through boom loading. That shuttle cycle keeps the coal moving without a pause, almost like the machines share the same timing. Once filled, the shuttle car travels out by and discharges its load for further transfer. Structural stability becomes the next priority. Roof bolt drilling units prepare the rock overhead, followed by roof meshing and bolting that secure the working area above the miners and machines. Gas management forms another layer of preparation. A drill rig performs long-hole drilling for gas drainage, while pipes channel the extracted gas safely away from the seam. At the heart of the system stands the long wall shearer. Along the long wall main gate, powerful supports hold the roof while the shearer drum slices across the coal face. Seeing that drum carved through a seam really puts the scale of underground mining into perspective. As the shearer advances, roof supports step forward one section at a time, allowing the operation to continue along the panel. Once the production cycle concludes, crews travel out by again toward the shaft bottom, where cages and drift dolly cars handle personnel, materials, and equipment moving back to the surface. How do massive concrete beams end up perfectly aligned to support high-speed railway tracks across long distances? Building that structure demands specialized bridge construction machines, massive precast beams, and carefully organized assembly along the railway line. Work on these bridges depends heavily on large precast concrete beams. Production yards prepare the beams in advance, so they can be transported directly to the construction site. Bridge launching equipment then lifts and positions each beam between piers to support the elevated railway structure. Because high-speed rail requires extremely stable track geometry, bridge structures provide important advantage. Elevated spans reduce interference from uneven ground and urban obstacles, while keeping the rail line level across long distances. Crews guide the long machines slowly along the completed section of the bridge. Each new beam is hoisted, moved forward, and lowered into position to extend the line step by step. Seeing those enormous beams settle perfectly brings a quick moment of surprise. Once the span is secured, the launching equipment advances to the next position, repeating the sequence until a continuous bridge line stretches across valleys, roads, and developed areas. Demolition engineers bring down a boiler house through controlled blowdown, turning a towering power station structure into collapsing steel and concrete within seconds. One breath later, wow, the entire frame folds inward exactly along the planned collapse line. "11 meters of asphalt laid in a single pass inside a tunnel sounds excessive, yet the Vogel Super 2100-3 asphalt paver handles the job without splitting the roadway into smaller sections. A single paving pass at that width removes alignment joints completely, which directly improves long-term road stability. Construction moves into the third tunnel tube, after the structure itself stands ready for roadway installation. Trucks deliver hot asphalt mixture, while a material feeder transfers the load continuously toward the paver. Constant feeding keeps the paving flow steady and prevents gaps in the mat. The mixture reaches the Vogel Super 2100-3 asphalt paver, fitted with an extended screed capable of covering the full 11-meter road width in one movement. The paver advances slowly through the tunnel, while the screed spreads and levels the asphalt across the entire carriageway. Placing such a wide lane in one pass removes the need for a center seam, a detail that usually becomes the weakest line on many roads. The material settles into a uniform layer, while compaction equipment follows behind to tighten the surface structure. A continuous supply of asphalt remains critical during this phase. The material feeder transfers each truckload smoothly to the paver hopper, preventing temperature drops and uneven placement. A short interruption could leave a visible joint across the roadway, so timing between trucks stays tightly coordinated. Then the scale of the result becomes clear. Wow, an 11-meter strip of pavement stretches through the tunnel without a single longitudinal joint. Wide paving like this reduces maintenance points along the finished road. The completed surface forms a continuous driving lane, prepared for high-speed traffic once the tunnel opens for service. A quay wall strong enough to anchor the world's largest bulk cargo vessels does not appear overnight. This documentary reveals how engineers constructed the towering structure supporting massive maritime shipping. Design planning laid the groundwork years before construction crews arrived. Engineers mapped seabed conditions, vessel sizes, and load forces to determine how the quay wall would support enormous ships filled with bulk materials. The target: create new berths strong enough for the largest cargo carriers. A wall holding back sea and ship weight at the same time. No room for guesswork here. Work on the foundation moved forward with heavy marine equipment stabilizing the seabed. Dredging vessels cleared massive volumes of sediment to create the required depth for deep draft ships. Barges then transported rock and structural material into position to prepare the base layers beneath the quay structure. Picture stacking layers strong enough to hold a floating city in place. Large structural elements followed. Precast concrete units and reinforced sections were installed to form the vertical face of the quay wall. Each section had to align accurately so cargo vessels could berth safely along the finished edge. Crane barges lifted these enormous elements into position, while divers and monitoring systems verified alignment below the surface. One misaligned block here could turn docking into a nightmare for ship crews. Behind the wall, massive backfill operations strengthened the structure. Layers of rock and aggregate were compacted to create a stable platform capable of supporting cargo handling operations and heavy port equipment. Drainage systems and reinforcement components were installed to manage pressure from water and soil behind the wall. All that hidden structure quietly carries the real workload. Surface infrastructure came next. The berth deck was constructed to accommodate cranes, conveyors, and truck traffic handling bulk cargo. Surface corridors and access zones allowed equipment and operators to maintain safe operations around the berth edge. Huge ships sliding alongside this wall later will look effortless, though the engineering effort underneath tells another story entirely. Final stages focused on testing and operational readiness. Engineers evaluated load capacity, settlement behavior, and structural stability to confirm the quay wall could support the largest bulk carriers entering port service. Whoa! Structures of this scale quietly hold back both the ocean and millions of tons of cargo at the same time. Once completed, the new berths allowed bulk vessels of unprecedented size to dock safely and efficiently. The quay wall stands as the structural centerpiece enabling high-capacity maritime cargo handling on a global scale. "10 tons of explosives solve the challenge of removing a hydroelectric dam threshold blocking the next construction stage. A moment like this compresses months of drilling and preparation into seconds. Boreholes line the rock structure, each loaded with measured charges. Detonation signals trigger simultaneously. Wow, that scale hits instantly. Broken rock clears the threshold area for the dam's next structural phase. How do flat corrugated steel plates transform into a railway bridge using the OptimPlate system? Delivery brings S235 structural steel sheets, each 6 mm thick, with 200 x 55 corrugation. Crews align segments and secure them using Class 8.8 bolts. A curved shell slowly appears from flat plates, engineering logic turning simple steel into structure. Scaffolding supports spray insulation work. Then comes the striking moment. Huge assembled sections slide forward along a temporary track. The completed corrugated bridge structure moves directly into the existing railway opening. Some expect poured concrete for canal lining, yet concrete canvas forms the channel wall using fabric and water. Work opens with site preparation and layout along the canal route. Crews position a drainage pipe along the base to guide groundwater away. A small pipe here saves a lot of trouble later. Channel profiling follows, shaping the bed and side slopes to match the required geometry. Next arrives the concrete canvas. Large rolls are lifted down the canal and unrolled across the prepared surface. The material spreads across the profile, adapting to curves and corners. The roll unwinds like a giant carpet dropped into a trench. Workers adjust alignment so the sheet sits flat along the slopes and base. Edges overlap along the joints. Bolts secure these overlaps at regular intervals, locking neighboring layers together. Each bolt clamps the fabric tight. No drifting edges once water arrives. Stakes then anchor the canvas along the channel edges, holding the lining firmly against the ground. Hydration transforms the flexible material into a hardened concrete layer. Water sprays across the entire surface, activating the cement within the fabric. Soft fabric today, rigid channel wall tomorrow. Over the following hours, the lining stiffens and bonds to the prepared canal shape. The completed structure protects the irrigation channel against erosion and soil movement. Water can move through the passage without wearing away the sides or base. A trench that once looked fragile now carries water like a built concrete canal. Large curved steel segments assemble into the turbine pit liner supporting hydroelectric turbine Unit 3. Unit 3 turbine pit liner installation inside a hydroelectric powerhouse reveals how heavy steel structure preparation shapes the final performance. Work begins with steel liner segments prepared to match the diameter required for the turbine chamber. Each curved plate is lifted into the pit and aligned along the circular wall that will hold the turbine casing. Every section must match the curvature perfectly, or the circle refuses to close. Welders secure the first liner plates directly to the surrounding structure. Heat arcs trace the seams where plates meet edge to edge. Bright weld lines crawl around the cylinder like glowing stitches holding the metal skin together. The liner slowly grows upward and downward as additional sections are added. Crews keep adjusting position and alignment while welding continues along vertical and horizontal joints. A few centimeters off here would echo through the entire turbine assembly later. Once the full liner ring is complete, additional weld passes reinforce the joints and seal the steel surface. The finished cylinder forms a durable inner wall ready to support the turbine installation inside Powerhouse Unit 3. A 481-ton FCCU regenerator head replacement demands crane lifts, skid systems, and millimeter-level alignment. One carefully engineered sequence replaces the old cyclone assembly with a new structure built to extreme dimensional accuracy. The upgrade centers on the regenerator head that carries cyclone separators inside the FCCU system. After decades of operation, the upper section of the regenerator vessel must be removed to allow installation of the new component. A structure this large turns every millimeter into a serious decision. Preparation begins with building a steel transport frame designed to support the old regenerator head. Self-propelled modular trailers move the frame into position beneath the unit. Nearby, a heavy skid system is assembled from two enormous steel beams. The beams guide massive components along a controlled sliding path toward the lifting area. Two beams quietly handling loads that outweigh entire buildings. Industrial scale shows up fast here. Meanwhile, the giant PTC crane is assembled piece by piece. Weeks of work raise the boom more than 100 meters above the unit, forming the main lifting tool for the replacement operation. Attention then turns to separating the existing regenerator head. A milling machine gradually cuts through the thick steel wall of the regenerator vessel, releasing the top section that contains the cyclones. Rigging equipment designed for this load is attached to secure the heavy structure for lifting. The old component is removed, clearing space for the new regenerator head that has already been transported to the skid bridge. The replacement section weighs roughly 481 tons and carries refractory lining and cyclone assemblies, 14 meters across and still expected to land within 10 millimeters. The crane slowly raises the massive head and positions it above the regenerator vessel. Lowering continues in small increments while alignment crews monitor clearances around the circular opening. Final placement takes close to 2 hours. Then comes the quiet moment. Everything lines up exactly where it should. After installation, additional lifting operations replace sections of the overhead line connected to the cracking unit. With the regenerator head secured and connections restored, the FCCU system stands ready for another long cycle of operation.
A single steel monopile heavier than 1,000 tons moves through the air, supported by 2 crawler cranes instead of one giant machine. Dual lifting distributes the enormous weight across both cranes instead of relying on a single hook. Monopiles arrive first and connect to long slings attached to both crane hooks. The machines raise the steel columns together and guide them onto a transport barge. Wow, that column hangs in the air like a steel tower. Balanced crane movement keeps the load level during positioning. A backhoe dredger can remove sections of solid seabed that once blocked ships completely. The crane lowers the bucket toward compact seabed layers, where rock, boulders, and old underwater structures remain buried. The bucket cuts into the material and lifts the load above the waterline for removal. That bucket rising full of broken rock almost feels like the seabed just gave up a chunk of itself. Operators repeat the digging cycle while the vessel maintains position above the dredging zone. One scoop after another and the stubborn bottom slowly opens up. Wow, that load looks serious. Many people imagine cranes arriving ready to lift, yet the Liebherr LTM 1400-7.1 requires a detailed assembly sequence before operation. A new unit arrives in transport configuration, with the carrier chassis supporting multiple telescopic axles and folded components secured for the road. Setup work unfolds in several deliberate stages. The carrier positions itself on firm ground while the operator prepares the stabilization system. Hydraulic outriggers extend outward from both sides of the chassis and lower toward the surface. Wide pads spread the machine's weight across the ground. The chassis rises slightly as the supports take the load and hold the crane steady for lifting tasks. Attention then shifts to the upper structure mounted on the slewing platform. The counterweight installation begins with large ballast plates delivered by support vehicles. One plate after another moves into position and locks onto the rear section of the crane. Counterweights balance the force created by long boom reach and heavy loads. The stacked plates gradually build the mass required for stable lifting. The telescopic boom system forms the next stage of preparation. Hydraulic cylinders extend the main boom sections upward from the base. Each segment slides forward from inside the previous section until the full length emerges. Nested boom sections allow long reach without increasing transport length. The structure now towers above the carrier frame, revealing the scale of the crane. A hook block assembly follows. Thick steel cables run through multiple sheaves, forming the lifting line that connects the boom tip to the hook block. Multiple cable passes multiply lifting strength across the system. The hook block descends slowly while the operator checks alignment and cable tension. Further adjustments continue around the machine. Technicians confirm connections along the boom head, verify cable routing, and secure remaining structural elements. Several components arrive on separate transport vehicles due to their size and weight. Bit by bit, the crane transitions from transport arrangement to full lifting configuration. Hydraulic systems power the steering of the carrier, as well as the movement of the boom and winch assemblies. The operator works from the control cabin mounted on the upper structure, guiding each motion through joystick commands. Control systems translate small hand movements into powerful mechanical action. The assembled Liebherr LTM 1400-7.1 now stands ready for heavy lifting operations. The long boom, stacked counterweights, and stabilized chassis combine into a machine designed for demanding construction tasks. Whoa! Seeing the crane rise piece by piece really changes the sense of scale. The setup stage reveals how a road-legal vehicle transforms into one of the most capable mobile lifting machines on a worksite. This CO2 frac unit forces open rock layers that once trapped energy deep underground. Pumps charge the line while valves stabilize flow, and the CO2 frac unit drives deeper. Four turbine generator units will rely entirely on this hydropower powerhouse structure to support 140 megawatts of electricity generation. This relocation sequence reveals how transporters move two 30-ton brewery vessels safely toward their brewing facility. Steel frames secure the cylindrical tanks while hydraulic axles distribute the load across the road surface. Crews guide the transporter through tight turning space, so the long vessels clear nearby structures. 30 tons rolling on wheels somehow looks lighter than expected. Multi-axle steering adjusts the trailer position to maintain balance while the convoy progresses step by step. Each correction keeps the brewery vessels stable during transport toward their installation site. Moving equipment this large across ordinary streets really puts scale into perspective. The relocation continues steadily until both vessels reach the brewery area, ready for lifting and integration into the brewing system. Sea trials reveal how the submarine S-81 responds to aerial control plane adjustments in open water. The vessel measures about 80 meters long and displaces nearly 3,000 tons underwater. Diesel, electric propulsion, and advanced control systems guide each maneuver. An oil tanker conversion project turns this vessel from an ore carrier into a crude oil tanker within 51 days. The vessel originally served as a very large ore carrier, yet engineers reconfigure the structure to operate as a crude oil tanker. Turning a giant ore carrier into an oil tanker feels like asking a skyscraper to change careers halfway through its life. Docking preparation positions the ship inside the repair basin, where hull inspections confirm structural conditions before modification. Technicians remove internal bulkheads and adapt cargo hold geometry so the compartments match tanker storage layouts. Reinforcement plates appear across selected sections of the hull to handle different loading stresses. Those steel plates sliding into place resemble puzzle pieces, built for machines the size of small towns. Piping teams install new cargo transfer lines and pumping equipment designed for crude oil transport. Control systems and monitoring equipment follow inside the cargo management spaces. Workers also adjust ballast systems so the tanker maintains stability during loading and voyage operations. The number of pipes alone could confuse anyone trying to trace where a single valve leads. Hull sections receive protective coatings suitable for oil service, while deck machinery undergoes upgrades for tanker operations. Final checks confirm cargo flow systems, pumps, and structural reinforcement before departure. 51 days later, the vessel leaves the dock with an entirely different mission. Wind turbine parts appear light in photos, yet a heavy transport trailer carrying turbine components handles enormous weight. The turbine section rests on a multi-axle modular trailer designed to distribute extreme weight across many wheels. That long blade section stretching over the trailer almost looks unreal at first glance. Hydraulic steering modules adjust the trailer direction while the convoy moves slowly through tight curves and intersections. Support vehicles coordinate traffic and guide the tractor driver through limited road space. Gradual braking, steering adjustments, and coordinated movement keep the wind turbine component stable until it reaches the destination. The scale hits differently once a regular truck passes beside it. A wind turbine installation using crawler cranes raises a power-generating structure taller than many buildings. Transport trailers position tower segments near the foundation, while crews prepare lifting points and alignment guides. Standing beside one tower ring quickly resets any idea of normal construction size. Crawler cranes raise each cylindrical tower section and lower it onto anchor bolts fixed in the concrete base. Technicians secure the flanges with large bolts that lock the structure into a vertical column. Next, the nacelle lifts into position above the tower before rotor blades attach to the hub. Seeing the full turbine assembled suddenly feels unreal. Truck haulage often gets linked with underground mining, but the rail-veyor ore transport system replaces many truck routes. A train of small two-wheeled rail cars moving rock along a light rail track powered by electric drive stations. The line of rail cars resembles a conveyor belt that decided to learn how to drive. Ore leaving the working face enters loading points, where broken rock drops into the connected rail cars. Each car links to the next, forming a continuous moving chain guided by narrow rails installed through the tunnel network. Variable frequency drive stations positioned along the route pull the train forward in controlled stages. One station hands the motion to the next. The rail cars climb steep underground routes that reach gradients close to 20%. Tight curves inside the mine corridors do not stop the convoy because the compact car bodies pivot easily along the track. A convoy of ore quietly sliding around a sharp corner feels strangely futuristic for such an old industry. Discharge stations receive the material at the surface or processing level where the rail cars tilt and release the load. The empty train then travels back toward the working face for another cycle. Suddenly, the scale of daily ore movement becomes very clear. Container yards don't run on cranes alone. The Hyster H22.00XM12EC empty container handler quietly handles the real stacking workload. The machine lifts a container from the ground, raises it above stacked rows, then aligns it into position for stable storage. Hydraulic steering guides the handler through tight yard lanes while the spreader locks onto corner castings for secure lifting. Seeing a steel box lifted that high really changes how container yards feel. Each placement adds another layer to the growing stack, preparing containers for the next loading cycle. One machine quietly organizing an entire field of containers. Without heavy haul trucks moving ore, the entire open-pit mining system would stall despite huge excavators and drilling rigs. Giant dump trucks climb spiral haul roads carrying blasted ore toward crushers and processing routes. Drilling rigs prepare new blast holes across stepped pit benches, while excavators load another truck cycle. That haul road spiral almost feels endless. Each trip extends the extraction chain deeper into the open pit, steadily removing layers of earth to expose valuable ore. Volvo F excavator quietly handles rock loading that would overwhelm many trucks without its bucket lifting massive chunks. The bucket lifts a heavy chunk. That single scoop carries serious weight. Another truck rolls forward for the next load. Offshore lifting reaches a different scale. Once the Sleipnir heavy lift vessel positions its twin cranes over massive structural sections. A floating platform arrives beside the hull, while the twin crane booms rise over the deck, each prepared for extremely heavy lifts. Loads reaching tens of thousands of tons hang from these hooks, turning the deck into a moving construction site. Preparation fills the early phase. Rigging crews attach giant slings and lifting frames to the structure, while the cranes adjust position. Hydraulic systems raise the booms gradually, aligning cables above the target. Every adjustment counts, because a shift of centimeters can change load balance across thousands of tons. The cranes then take the weight. Steel cables tighten, lifting the structure clear of its support frame. Slowly, the suspended load travels across the water toward its installation point. Seeing such scale glide through open air feels unreal for a moment. Control stations regulate hoist speed, boom angle, and load distribution between the two cranes. Variable speed drives coordinate motion so both sides carry balanced force. Once aligned above the foundation structure, the cranes lower the load in measured increments. One last descent settles the massive component into position, turning an empty space into working infrastructure. The Sleipnir vessel then resets rigging for the next lift, repeating the cycle that shapes offshore construction piece by piece. A ship becomes a floating parking structure through the brake bulk vehicle loading system on a car carrier vessel. Heavy equipment, industrial modules, and large transport vehicles line up at the terminal ramp waiting for entry clearance. The scene feels more like a rolling convoy than traditional cargo loading. Access to the vessel happens through a reinforced stern ramp connecting the dock to the internal deck. One vehicle at a time climbs the ramp while deck crews guide alignment using marked lanes. A fully loaded transporter slowly climbing into a ship can feel surreal for a moment.
I don't think I can take this anymore. I might just break. All the way hard and
Once inside, drivers steer toward assigned parking zones designed for different weight classes. Large cargo carriers settle into reinforced deck sections, while smaller trucks fill surrounding lanes. Wheel chocks lock against the tires and steel chains attached to dedicated lashing points on the vehicle frame. Those chains quietly handle enormous forces once the ocean starts moving the ship. Cargo planners monitor spacing and deck load distribution to maintain vessel stability. Drivers shut down engines, step away, and the securing teams finish tightening every restraint. Rows of industrial machines now sit inside the hull like a parking structure built for giants. After inspection confirms each vehicle is secured, the vessel departs carrying brake bulk cargo across long sea routes. See how a cruise ship grows from steel plates into a floating resort. Each block already contains corridors, pipes, and cable routes, turning raw steel into a functional structure early. Heavy transporters move the completed blocks toward the assembly dock. Giant sections stack layer by layer until the hull outline appears. LNG propulsion modules and engine systems slide into prepared compartments beneath the main deck. Energy systems based on LNG reduce exhaust emissions compared with conventional marine fuel. Interior modules follow next. Cabins, stair sections, and service areas enter the hull as prefabricated units. Workers secure them to structural frames, while electrical and ventilation connections link each section. Walking inside at this stage feels like entering a floating city still under construction. Interior spaces, technical decks, and passenger facilities now operate within a single floating structure assembled from hundreds of steel sections. Painting, testing, and system integration complete the vessel before final delivery. Global container trade would slow dramatically without automated STS cranes handling mega-vessel unloading at modern terminals. These cranes raise multiple containers at once and pass them to a fully automatic portal trolley racing along the crane beam at high travel speed. Several steel boxes travel through the air in one movement, port logistics scaled to another level. The trolley transfers containers toward horizontal transport vehicles heading to the yard. There, automatic stacking cranes receive the units and organize them in stacks reaching 6 containers high and up to 10 wide. A container stack suddenly looks like a steel apartment block. Automated systems identify each container and confirm door direction before placement. During lowering, crane drives regenerate energy, returning a large portion of power back to the electrical system. Operators mainly supervise exception alerts from control stations, while intermodal yard cranes transfer containers between yard blocks and rail tracks, keeping the terminal running continuously.